Now we're at stop number 7. So here we are. We've been following the layers. Hopefully you'll have a chance to look at some of these during the lab. Start to look for some interesting features. There's a lot in here, but I try not to beat you over the head with it because there's a lot happening here. And then suddenly, I want you to take a look at, compare what is on the right side of your screen with what is on the left side of your screen. And ask yourself, do these layers match? Does this look like continuous layering across the screen here? No. This is a textbook example of what a fault looks like cutting through sedimentary rock. So we're going to take a closer look at this fault. I'm going to show you, we're going to get up a little closer to it. I've seen a couple places where there's clearly rock falls in progress, so I'm not getting too cozy quite yet, but here we go. So what you see here is clearly layers that are continuous and then they're suddenly not. Often the actual fault itself will have quite a bit of vegetation. You can also see an increase in the number of fractures. You're starting to see fractures with offset. Now let's see, and so we know the fault cuts across the Scripps Formation. Now if you've been looking a little closely at the top of the cliff, you might notice that's not the Scripps Formation. That is probably Bay Point up there at the top. And the question is, does the fault cut through the Bay Points? And that'll help you constrain the age of the fault, because the fault has to be younger than what it cuts through, and anything on top of that erosion surf, and if the fault is eroded, anything on top of that has to be younger than the fault. And you use this technique all the time to figure out when a fault last moved and determine how active that fault is.